Hey everyone, welcome back to Boon Channel. In the last episode, we stood up a multi-user JupyterHub on our Kubernetes home lab, wired SSO with Keycloak. Today, we're going to start building the open data stack on top of that foundation, beginning with data ingestion. Here's the plan. We'll add two key building blocks to the cluster: MinIO for object storage, and Lakekeeper to manage our Apache Iceberg catalog. Then we'll walk through a few ways to bring data in. Point and click with Airbyte, lightweight Python pipelines with DLT, and orchestrated jobs with Airflow or Dagster. By the end, you'll see how each tool fits, when to use which, and how they all land data reliably into Iceberg-backed storage in your cluster. If you've been following along, you should already have the base cluster, Ingest, and JupyterHub running. If not, I'll flag the prerequisites as we go. The goal for today is simple: get a real dataset flowing into MinIO and Iceberg, keep it reproducible, and set ourselves up for incremental loads so the next episode's on transformation and serving plugins smoothly. Quick disclaimer before we go deeper. This series targets application development and small or solo teams. We're building an OSS self-hosted stack here, but that's not a universal prescription. Managed cloud services can absolutely be the right call as you scale. Our focus is the technology path: wiring components, showing configuration, and making data flow. We intentionally gloss over full-strength security hardening, governance processes, and organizational roles. Treat what you see as a learning baseline you can harden later, or even migrate from if you decide to adopt managed services. For a production-grade platform, consult additional references on security, governance, and operational maturity. All right, with that scoped, let's dive in. In a sentence, the open data stack is the modern data stack, built with open source software. At a high level, it covers how we ingest data, transform it into usable shapes, and serve it to applications and people. In this series, we're assembling that stack on Kubernetes, end to end, so you can run it locally or port it to the cloud later. Next, let's talk about why this matters in modern app development. Over the last few years, more and more apps have effectively become data apps. Two shifts are driving this. First, AI features. To make LLMs genuinely useful, we need two things: supply additional context via RAG, and allow safe access to application capabilities via MCP. That's why data integration matters here, so the model can see the right information and invoke the right actions under control. Second, products are increasingly event-aware. User interactions are captured as streams or events that feed downstream processing, recommendations, and analytics, often in batches or near real time. That's the job of the open data stack. It gives us a consistent way to ingest, transform, and serve data built on open components so you can run it locally in a home lab or port it to the cloud later. In this episode, we set up storage first, then build the ingestion path. We'll cover transformation and serving in later episodes. We're using MinIO for object storage and Lakekeeper for the Iceberg catalog. MinIO gives us an S3-compatible endpoint inside the cluster. The same semantics your code would use against AWS S3, but local and fast. That means anything we prototype, Airbyte targets, DLT loaders, or future Spark Trino queries, can later point to a cloud bucket with minimal change. Installing MinIO here is straightforward. If you're using Boonstack, run just MinIO install. Doing it by hand? The just file in the MinIO directory shows the Helm values and steps. If you expose services through Cloudflare Tunnel, add a public hostname for the MinIO API and console. Authentication is integrated with Keycloak, and you can also manage access policies directly there in the Keycloak admin UI. Now let me show the bucket and credentials setup in the MinIO web console. First, open the MinIO web console in the browser. Click Login with Keycloak and sign in. In the left menu, click Access Keys, then click Create Access Key. Leave defaults and click Create. Copy the generated access key and secret key and keep them safe for this demo. Next, in the left menu, click Buckets, then click Create Bucket. Enter sample as the bucket name and click Create Bucket. From the command line, we interact with MinIO using the MC command. If you are on Mac OS, you can install it with Homebrew. Next, we configure an MC alias, so the command line can talk to this MinIO endpoint using the keys we just generated. MC alias, set, alias name, MinIO endpoint, access key, and secret key. Now we can list the buckets in MinIO. I've got a sample CSV file locally. We'll upload it into the sample bucket. After that, you can list it with MC or confirm visually in the MinIO web console. Next, we need an Iceberg catalog, so raw files become managed tables. Lakekeeper is a lightweight Iceberg REST catalog shipped as a single Rust binary. It integrates with your OpenID provider and can also authenticate Kubernetes service accounts. It is stateless and easy to scale. Its design is modular. Catalog backend, secret store, authorizer, change events, and contract verification can be swapped or extended. So small teams get a simple start while retaining a path to stricter policy later. In Boonstack, you install it with just Lakekeeper install. The just file in the Lakekeeper directory shows the Helm values and steps if you want to do it by hand. Now I will walk through the Lakekeeper console setup. Open the Lakekeeper URL in the browser. Click Login, and sign in with your Keycloak account. In the top right, click the user icon, then click Create Token. An access token is generated and copied to the clipboard. Store it safely for use in API calls or CLI later. In the left menu, click Warehouses, then click Add Warehouse. Enter the following: warehouse name, sample. Click AWS S3, credential type, access key. AWS Access Key ID is the MinIO Access Key ID you created earlier. AWS Secret Access Key is the MinIO secret key. S3 flavor is S3 compatible storage. Bucket region is US East 1. Enable path style access must be on. Bucket is sample. Endpoint is http minio.minio:9000. Click Submit. After Submit, you should see the sample warehouse listed. This binds the catalog to the MinIO bucket so we can create Iceberg tables over the files that land there. Now let's switch into Jupyter and use the catalog from code. First, I'll open a notebook that stores secrets. In Boonstack, we use a small helper called Secret Store. It stores secrets in HashiCorp Vault, so we do not hardcode keys in notebooks. On cloud platforms, you would use AWS Secrets Manager, GCP Secret Manager, or Azure Key Vault. We create two secret entries, one for MinIO and one for Lakekeeper. I will operate the catalog with PyIceberg. On screen is the notebook that uses PyIceberg to create a table, append data, and run a scan. The first cell imports the PyIceberg REST catalog client, plus arrow, pandas, and datetime. The next cell creates the secret store instance. Then we read the MinIO endpoint, the access key ID, and the secret access key. We also read the Lakekeeper URL and the API token and set the warehouse name and the namespace. Next, we will create or verify the namespace through the catalog so that the table has a logical home. After that, we define a schema with the field's ID, name, price, category, and created at. Then we create the table if it does not already exist, so the catalog tracks its metadata. We build a small set of rows in a data frame, convert it to an arrow table, and append it to the Iceberg table. Finally, we run a scan and apply a filter for price greater than or equal to 100 to confirm we can read back only the matching rows. Now when we append and scan, the data files and metadata are written under that bucket path, and Lakekeeper tracks the table state. Filtering with an expression returns only the higher priced rows. Now we move into ingestion. I will show 4 approaches: Airbyte for point and click SAS ingestion. Pure DLT for a lightweight Python-only pipeline. DLT inside Airflow to schedule and coordinate runs. DLT inside Dagster to model assets and lineage. We start with Airbyte, then a direct DLT run, Then wrap the same DLT logic in Airflow, then in Dagster to compare ergonomics. Let's look at Airbyte. It starts with a big catalog of SAS connectors. Many sources run without writing code. When you need something missing, you have 3 build paths. The builder in the UI can get a simple connector working in under 10 minutes. The low-code CDK is declarative, a small YAML-style spec that covers stream definitions, endpoints, pagination, and cursors for many APIs without writing code. When you truly need custom logic, you step up to the full language-specific CDKs, which take longer, maybe a few hours, but give full control. Each sink launches its own source and destination containers. That isolation means we can upgrade or roll back a single connector version without touching others, and crashes stay contained. The trade-off is extra startup time and more CPU and memory than a single in-process script. The web UI handles setup and monitoring. You create a connection pick source and destination set sync frequency and watch logs retries and emitted records. Now I will install Airbyte. First, Airbyte is not part of the default Boon stack core right now. To enable the recipes, we copy 2 things. Copy custom example.just to custom.just. Then, copy the custom example directory to a new custom directory at the root. After that, we can list the custom Airbyte tasks. You should see the Airbyte-related recipes printed. That confirms the tasks are wired. Next, we run the install command. During install, a prompt asks whether to set up OAuth 2 proxy. If you will expose Airbyte on the internet, you must enable it. The self-hosted OSS version of Airbyte does not ship with built-in authentication integration. We place OAuth 2 proxy in front, so Keycloak handles login. After authentication, every user lands in the same shared Airbyte workspace. There is no per-user isolation. Keep that in mind when naming connections or handling credentials. Once the install completes, open the Airbyte URL. Before creating a destination, we must upgrade the built-in S3 connector so it can target MinIO. Versions 1.9.1 and earlier failed during destination creation against MinIO, so we bump to 1.9.2. In the left menu, click Settings. Click Destinations. Scroll down to S3, and on the right side, click the Edit icon. Find the Docker image tag field. It shows 1.9.1. Change the tag to 1.9.2. Click Submit. The S3 destination connector is now updated and ready to point at MinIO without errors. Now, we will create the S3 destination that points at MinIO. In the left menu, click Destinations. In the search field, type S3. 2 entries appear, S3 and S3 Data Lake. Click S3 Data Lake first to inspect it. You can choose catalog type REST catalog, but there is no place to configure authentication, so we cannot connect Lakekeeper directly now. It would be ideal to ingest straight into Iceberg, but we will land raw data in MinIO and convert to Iceberg during a transform step later. Click Back. Click S3. Fill the form. Access key ID. Secret access key. S3 bucket name. Sales. S3 bucket path. Sales. S3 bucket region. US East 1. Output format. Parquet. Compression codec. Snappy. S3 endpoint. HTTP minio.minio9000. Click Setup Destination. The S3 destination backed by MinIO is created and ready for a connection. Next, we will create a Salesforce source. In the left menu, click Sources. In the search field, type Sales. Click Salesforce. Enter the client ID and client secret. There is a button, Authenticate your Salesforce account, but that runs the OAuth 2 flow. Our Airbyte is protected by OAuth 2 proxy, so Salesforce cannot call the callback URL, and we cannot use it. Click Set up manually. Paste the refresh token, which you must generate manually by running this command. Click Setup Source. Next, we will create a connection between the Salesforce source and the S3 destination. Click Create your first connection. Select the Salesforce source. Select the S3 destination. Wait while the schema is processed, then the schema selection screen appears. Clear all selected schemas and enable only account for sync. Click Next. Set schedule type to manual. Set schema to source defined. Click Setup Connection. When the connection page loads, click Sync Now in the top right to run a manual sync. Wait until the sync finishes and shows a success state. Now verify the file landed in MinIO with MC. Copy the Parquet file locally and inspect the rows. We confirm the Parquet file was written correctly into MinIO. We also need to look frankly at limits of self-hosted Airbyte in this stack. Authentication. The open source edition cannot directly integrate an identity provider for per-user control inside the application. We must front it with OAuth 2 proxy. After login, every user lands inside the same shared workspace. No isolation. Overhead. Each sync starts separate source and destination containers, plus control plane services. Many official connectors run on the JVM. This adds cold start time and consumes more memory and CPU than a single in-process Python script for a comparable custom job. Memory behavior. With very large datasets, memory use can keep climbing. When trying to ingest the MovieLens 20 million row dataset from MinIO to PostgreSQL, the run did not finish even after allocating 20 GB of memory. I looked for a clear, built-in knob to cap connector memory or a recommended Java garbage collector tuning flag set in the official docs, and did not find a reliable workaround for this pattern. Extension path. Although Airbyte offers 3 ways to build a connector, once we reach the point of writing real logic, other code-first tools like DLT feel faster to iterate with. So in Boonstack, Airbyte remains an example, not a core service. It is useful to demonstrate quick point and click ingestion and connector catalog value. The core flow leans on code-first tools for day-to-day pipelines. Next, we will look at ingestion with DLT and a short overview of why it fits this stack. DLT is an open-source Python library for loading data. It infers schema, normalizes data, and handles nested data structures. It is orchestrator-friendly. The same code is straightforward to embed in Airflow or Dagster projects, even though they are separate tools. It automates pipeline maintenance through incremental loading, schema evolution, and simple data contracts. Next, we will create an ingestion pipeline with DLT. The demo project for this pipeline is here on screen. In this project, we pull data from Salesforce and write it into Lakekeeper, which serves as the Iceberg REST catalog in this stack. The scaffold came from this single command. That generates a Python package under a Salesforce directory. For the source side, we only supply configuration values. DLT handles the API extraction logic for the standard objects. For the destination, we implemented a custom destination that talks to the Iceberg REST catalog. The open-source DLT distribution does not ship a built-in Iceberg REST destination. This shows that you can extend it and still reuse the core pipeline machinery. If your workflow prefers to convert to Iceberg later during the transform phase, you could instead point the destination at MinIO and land raw Parquet or JSON files now, then build tables in a follow-up step. That is the simpler path if you do not need table semantics immediately. This load function is the entry point that runs the pipeline. It reads the environment variable write disposition, which we allow to be either default or force replace. By default, each Salesforce object type has an assigned write disposition. Some are handled as replace, others as merge. When force replace is set, we override that mapping and treat every resource as replace, and we clear prior run state so the load behaves like a fresh, full snapshot. The pipeline definition is here on screen. The destination argument, Iceberg REST catalog, is the custom destination we showed earlier for Iceberg REST catalog. The source configuration shown here only narrows which Salesforce object types to pull. Finally, the invocation of the pipeline happens in this call section at the bottom. To run this, we define environment variables in a .env.local file as described in the project README. Instead of writing secrets directly, we store 1Password item references and use the CLI to inject them at runtime. We run the pipeline with this command. One friction point. The exact environment variable names for DLT sources are not always explicitly listed in official docs, and they are generated dynamically from Python code. The repo includes a helper script that dumps the environment variable names for a given source. You can run it like this. If your Salesforce organization does not contain suitable sample data, there is a recipe under the data directory to generate and import fake records. It uses Snowfakery plus Cumulus CI to load realistic-looking objects into Salesforce. You can review that recipe and run it before executing the pipeline so that the tables are populated with meaningful test rows. Now we will run the pipeline. The run completed successfully. Check the created tables with this script. That confirms the destination catalog contains the expected Iceberg tables registered through the custom destination. We ran the pipeline directly as a one-off process. That works for ad hoc loads and development, but breaks down as soon as we need guarantees. We need a scheduler to run at fixed or event-based intervals. We need dependency control so extract steps finish before downstream transformations or model refreshes. When a run fails, we want retries and alerts, not a silent exit in a terminal window. We also want to manage parameters and credentials cleanly across multiple environment settings. That is the role of an orchestration tool. We will first wrap this same DLT code in Airflow to show a classic DAG-oriented scheduler. Then we will express the same logic in Dagster to show an asset-centric approach with strong metadata and lineage. The underlying DLT resource code stays almost the same. We only adapt entry points and configuration wiring. Next, we start with Airflow. Airflow is the most used open-source orchestrator. Pipelines are authored in plain Python. Dynamic generation is easy, and Jinja templating lets you render parameters dynamically at runtime. The provider's ecosystem supplies many operators and hooks for databases, cloud services, and SaaS APIs, so you write less repetitive integration code. The web UI shows run status, task logs, and a graph view of task dependencies. Airflow itself ships deep integration points for many services. But today we focus on embedding the existing DLT pipeline as a single Python task, so we keep the same code and CLI workflow while gaining scheduling, retries, and observability. Now I will install Airflow. Run the install task. During install, you are asked, enable DAG persistence with PVC? Choose yes. This creates a persistent volume claim for DAG files, so they persist and can be shared across pods. Next, assign a role to your user. For this demo, assign the admin role to the user Boone. Open the Airflow URL in the browser and log in with your Keycloak account. In the left menu, you should see Admin, which confirms admin privileges. You can also manage this role mapping from the Keycloak admin console. If you created the DAG PVC, you can edit DAGs from JupyterHub. Reinstall JupyterHub, and when prompted, enable Airflow DAG storage mounting, choose Yes. The DAG directory will be mounted into Jupyter under a folder named Airflow DAGs. Note that this DAG directory is shared across users, so coordinate edits and naming carefully. Now we will run the DLT pipeline from Airflow. First, return to the DLT demo project directory, then move into the Airflow directory. The Airflow DAG is implemented in DAGs, Salesforce, Iceberg, dag.py. The DAG definition begins here. The first task, validate configuration, checks environment values. It verifies that 7 required variables for the DLT pipeline are set either as pod environment variables or as Airflow variables. The next task, run Salesforce pipeline, sets the needed environment variables and executes the pipeline. The task verify data load checks the Iceberg catalog to confirm the expected state. Finally, the task print result prints a short summary of the outcome. Now set the required environment values. There are 2 ways. One is to create a Kubernetes secret named Airflow env secret. When this secret exists, its key value pairs are injected as environment variables into the Airflow pods. This requires redeploying Airflow to pick up changes. The other way is to set variables from the web UI under admin, variables. This does not require redeploying Airflow. For this demo, we use the second option and create the variables in the UI as shown on screen. Go back to the console and generate the deployment files with just prepare. This creates the files needed under the local DAGs directory. Copy these into Airflow's DAGs directory. You could copy with kubectl-cp, but here we will use the JupyterHub mount. Open JupyterHub and drag and drop both items into the Airflow DAGs folder. Airflow will detect the new DAG and show it in the web UI shortly after. After a minute, refresh the Airflow web UI. You should see a new DAG named Salesforce Iceberg DAG. Click Trigger to start a run. When it finishes, open the task, Run Salesforce Pipeline to view the logs. Some DLT messages are logged at error level and show in red, but the run still completed successfully. Alright, we confirmed the DLT pipeline runs in Airflow. Airflow can add scheduling, retries, and logging around the same DLT code. It integrates with Kubernetes and supports Keycloak with role mapping. If you want a full-featured orchestrator in your cluster, Airflow is a solid choice. Next, let's look at the same pipeline in Dagster to see the asset-first take on orchestration. Dagster centers on assets, not just tasks. You model tables and files as assets and the code that builds them. That makes asset state clear and gives lineage over assets instead of only task dependencies. It has a fast development loop. You can start a local server with DG dev without a production deploy. You can run jobs from the CLI with DG launch. You can scaffold code quickly with DG scaffold. It fits with DLT and DBT. You can represent separate DLT or DBT pipelines as multiple assets. In a task-oriented orchestrator, those pipelines often collapse into single tasks. In Dagster, they remain first-class assets that you can track, schedule, and reason about individually. On Kubernetes, there are a few practical issues. The official Helm guide is here. Step 1. Write and build a Docker image that contains your Dagster project. Step 2. Configure kubectl to point at your Kubernetes cluster. Step 3. Add the Dagster Helm chart repository. Step 4. Configure the Helm chart for your deployment. At this step, you reference the image and the project definitions you built in Step 1. Step 5. Install the Helm chart. In practice, each new Dagster project means a new image build and a Helm redeploy. You cannot just drop a project into a running environment the way you can with Airflow. Also, the open source edition does not include OIDC or OAuth integration. If you expose the UI on the internet, you need to protect it with a reverse proxy such as OAuth 2 proxy. In that setup, the application state after login is shared across users. About the redeploy problem, I will show a workaround shortly. Before we install Dagster, there are two quick preparations. First, define the Python packages your project needs. Second, set environment variables via a Kubernetes secret. There are two ways to install extra Python packages. One option is to install packages in an init container when the pod starts. Add this to your .env.local file. Alternatively, build a custom image. Set these in .env.local. Then build and push the image. For this demo, we'll use the init container method. Next, define environment variables via a Kubernetes secret. In this demo, we'll use an external secret that reads from Vault and materializes a secret named Dagster.env secret. Apply a manifest like this. Now install Dagster in Boonstack with a single command. Open the URL, log in with your Keycloak account, and you should see the Dagster UI. Next, prepare the Dagster project. Return to the DLT demo repository. Inside the Dagster directory, there is a Dagster project that runs the DLT pipeline. It was generated by an LLM and not at all ideal, but today we only confirm how to run the pipeline in Dagster. In the Dagster directory, run just prepare to copy the DLT pipeline code into the Dagster project. Move to the Boonstack directory and deploy the project with this command. This copies the project into the Dagster pod with kubectl and updates the config map that stores workspace.yaml. In the web UI, open deployment. Wait a moment. You should see dlt_salesforce.definitions appear. This gives you a way to deploy a new project dynamically without a full Helm redeploy. Now let's run it from the UI. In the top menu, click Assets. Click View Lineage to open the asset graph. Click Materialize All to start a run. After a moment, all assets are materialized. Click an individual asset to open its page and review the logs for that materialization. We confirmed the DLT pipeline runs in Dagster. Dagster is asset-centric and pairs well with DLT and DBT. The CLI makes local dev and scaffolding quick. There are trade-offs today. The OSS edition has no built-in SSO, so put a reverse proxy in front of the UI. And each new project typically means a Helm redeploy, unless you use the dynamic deploy workaround we showed with just Dagster deploy project. If Dagster adds SSO support and a Kubernetes operator with custom resources to deploy projects, it becomes the best fit for our stack. Until then, if you mostly treat the orchestrator as a scheduler around DLT or DBT, Airflow can be the more practical choice due to its Kubernetes integration and SSO support. Today, we stood up the storage and catalog layer with MinIO and Lakekeeper, then ingested a real dataset two ways, point and click with Airbyte and code first with DLT. We wrapped the same DLT pipeline in Airflow and Dagster to compare orchestration ergonomics. Airflow brings mature Kubernetes and SSO support. Dagster brings an asset-first model and a fast dev loop. Thank you for watching.